Hi everybody, it's Mr. Ray here with our next lesson in grade 12 data management. We're working in the unit 5, which is looking at the normal distribution, which is um, the most widely used distribution we have in the real world. It applies to so many things. We're going to actually use it for a slightly different thing, and that's we're going to take a trip back a couple of units when we looked at the binomial distribution. If you remember, the binomial distribution worked on success versus failure. You had a probability for both of those. We called them P and Q. We had a certain number of trials, and basically the calculation was fairly straightforward. We had to use a combination. The number of ways we could, for example, if we had a question, what's the probability of a basketball player making 7 out of 10 free throw shots, given that he had a certain probability of, say, 60% of making each shot. So we could apply the formula for the binomial distribution. It worked quite well. Today we're actually looking at how we can actually use the normal distribution to very closely approximate the binomial distribution. So you might be thinking at this point, well, why are we coming up with another method of doing something that works pretty well? The questions we had for the binomial distribution were, kind of, they were thought in advance to make the questions not too difficult. So if you remember, if you wanted to do a calculation with the basketball player, what's the probability that the player makes more than seven or more shots out of the 10? Then it's basically you're doing a calculation for the random variable x being 7, and then another one for 8, another one for 9, another one for 10, and you just sum them all together. So that worked fairly well. But what if you have some huge range of numbers that you want to test for? For example, if I change the question to, if the basketball player took 200 shots, what's the probability that he or she is successful on somewhere between 120 and 150? So there's no way around it. You have to do at least 50 calculations or more, and that's a lot of time. So this approximation that we're going to learn today is for those situations where it's just too labor intensive to use binomial distribution, although you could, but this is a much faster way of doing it. So the key concepts here: as the number of trials increase, basically that's your value of n, a binomial distribution takes on the characteristics of a normal distribution. A discrete binomial probability distribution, remember binomial distributions are always discrete, can be approximated with a continuous normal distribution as long as NP and NQ are both greater than 5. So in order to, before we actually use this, we always have to test the value of n times p and n times q, and both of those have to be more than 5. If they're not, basically the data would be too unreliable for us to approximate with the normal distribution. Once we've confirmed that that's true, that we can go ahead and use, we have formulas to create the mean and the standard deviation, which we do need for the normal distribution. So the mean will be just n times p, which we've already calculated up here, so work's already done, and standard deviation will be the square root of n times p times q. So pretty straightforward formulas. We just have to test if we can go ahead, calculate our mean and our standard deviation, and then proceed as normal, as though instead of it being a binomial distribution, we've now changed it to a normal distribution. Okay, and this is important here, as with other discrete data, which we will be having, because these are basically binomial distribution type questions. We have to apply the continuity correction when approximating. So all of our examples will be showing how to do that if you've forgotten, but that was kind of what we were doing last lesson. Okay, so first question, Suzette rolls a die 36 times. She records the number of times the die shows a 6. Show that we can use the normal approximation to determine the probability number of times a 6 is rolled, okay? So, and then there's 3 different questions about probability that the dice shows a 6 a certain number of times. So before we get there, let's do our due diligence here. So our n value is the number of rolls, which is 36. Okay, p is the probability, so that's the probability of rolling a 6. Sorry, that's the probability of success, that's 1/6. And therefore q will be 1 minus 1/6, 5/6. Probability of not rolling a 6. So let's do our NP. We're testing to see if we can use this. So n, that's 36 times 1/6 is 6. So that is greater than 5. So far so good. And then NQ is equal to 36 times 5/6. Obviously this is going to be much bigger than NP. It's actually equal to 30. And 30 is bigger than 5 as well. So there's our second check accomplished. So what that means is we can go ahead and use the normal approximation. Okay, so let's set this up as a normal distribution. We need a random variable x. It's going to be the number of times a 6 is rolled. Okay, and let's get our mean and our standard deviation. So our mean is NP, which we already got calculated up there. It's 6. And our standard deviation, sigma, is equal to square root of NPQ. It's 36 times 1/6 times 5/6, all square rooted. That ends up being equal to 2.236. Okay, so now we're ready to go. So question A, got all the information we need. So question A says, well, it's not A, but it's first part says, what's the probability that the die will show a 6 more than 10 times? Okay, so this is, you might think that I'd put probability x is greater than 10, but remember we're changing discrete data into continuous data. So if I want it more than 10, I'm actually looking at x greater than 10.5. So probability that x is greater than 10.5 is what I'm looking for. That is, we have to change the 10.5 into a z-score, which we know from our formulas from quite a few previous lessons. That's going to be the x value, which is 10.5. Minus 6, which was the mean, over 2.236. So call this Z1, because we're going to do a couple of different z-scores. This is equal to 2.01. So there's our z-score. So now I just changed the probability statement to a z-score greater than 2.01. Now remember, with z-score we want it to be less than the value, so we have to do our switch over here. 1 minus the probability that z is less than 2.01, which is 1 minus. And if we look this up on the z-score, we get a value of 0.9778. So take that away from 1, we get 0.022. Okay, we'll do a word answer at the very end. So that's basically a 2.2% chance that 6 is rolled more than 10 times. Part B. So what's probably a die will show a 6 fewer than 10 times. So less than 10 times, again, it's not going to be x is less than 10. It's going to be x is less than 9.5. times, because what we haven't covered here, not between 9.5 and 10.5, would be the probability of rolling it exactly 10 times, which is the third part of the question. So we will be doing that as part C. Okay, this one's a little bit better. We do have to convert to a z-score. So we change 9.5 minus 6 for 2.236, and that works out to 1.56. So this is the probability that the z-score is less than 1.56, which is 0.9406. So pretty high probability that 6 is rolled fewer than 10 times compared to more than 10 times. Okay, now we do the last part. What's the probability 6 is rolled exactly 10 times? So this is where we go for the continuity correction again. So we're looking for x being between 9.5 and 10.5. Okay, now we've already got those z-scores. So that's going to be probability that, so 9.5. Z-score is greater than 1.56, but less than 2.01. And hopefully you remember from the last lesson, when we have this interval that we want the z-score or the probability for, it's the probability of the z-score less than the higher value minus the probability that the z-score is less than the lower value. So probability z is less than 2.01 minus the probability z is less than 1.56. So that's, we've got our values from the previous two questions. So 0.9778 minus 0.9406, which is 0.037. Okay, so if you add these probabilities up, you will get extremely close to 100% or 1. And that's the way it should be, because we've covered all the possible cases with A, B, and C. So hopefully this shows you how you would answer any of these questions, greater than, less than, or equal to. Okay, so therefore, there is a 2.2% chance of rolling a 6 more than 10 times. A 94.1%, just round that one a little bit, of rolling a 6 less than 10 times. And a 3.7% chance of rolling a 6 exactly 10 times. And if you do add up these three probabilities, you will get exactly 100%, which is the way it should be. Okay, so hopefully that shows you how you would use this approximation. So a question that looks like it is a binomial distribution, and is, you would first test the values of NP and NQ, make sure they're more than 5. And then there's formulas here for the mean and the standard deviation using NP and Q. Get those and then turn it into a normal distribution problem like you would normally would do from the previous lessons. Okay, I'll do a couple more examples just to get the hang of this. All right, a bank has found that 24% of its loans to new small businesses become delinquent. That means they're not paid. If 200 small businesses are selected randomly from the bank's files, what's the probability that at least 60 of them are delinquent? Okay, and it's got a comparison here, which we're not going to do, but we'll talk about. Okay, so let's gather the binomial distribution variables here. So we know that we're selecting 200 businesses, so n is 200. The p, in this case, probability of success, well, we're trying to find the number that are delinquent. So p is the probability of being delinquent, which is the 24%, or 0.24. Q is 0.76, 1 minus p. And then we'll do our checks. So NP would be 200 times 0.24, which is 48. Okay, well that's greater than 5, so that's good. NQ will be 200 times 0.76, that's obviously going to be higher. So that's 152, which is also greater than 5. So that's good. That means that we can go ahead and use the normal distribution approximation here. So I have to set up a random variable like we always do. X will be the number of delinquent loans. Okay, and let's figure out our mean and our standard deviation. NP, which we already calculated, is 48. And our standard deviation is square root of NPQ. Okay, I won't put those in, but it's 200 times 0.24 times 0.76, all square root. That's 6.04. Okay, so we want to know the probability that at least 60 of them are delinquent. So that means 60, 61, 62. That's assuming you're using a binomial distribution, a discrete distribution. We have to do the continuity correction because normal distribution is continuous. So instead of saying x greater than 60, we have to say x probability that x is greater than 59.5. Okay, and that's going to change into a z-score, so we have to convert that here. So the z-score will be equal to the x value we're testing for, minus the mean over the standard deviation. It's equal to 1.90. Running off the edge of the paper there. Okay, so that's the probability that z is greater than 1.90. And again, z-score, we have to have z is less than a value because it's to the left of the curve. So that's equal to 1 minus probability z is less than 1.90, which if I just skip a step here, this value here is like 0.971, so the whole thing is 1 minus that is, sorry, 0.029. So that means, therefore, the probability that at least 60 of the loans are delinquent is 2.9%. Okay, let's do one more example, two-part question, but very similar to what we just did in the first two examples. This one's Coca-Cola, a soft drink company, knows that it has a 42% market share in one region of the province. Coca-Cola's marketing department conducts a blind test of 70 people at the local mall. So we're being asked, what's the probability? Fewer than 25 people will choose Coca-Cola and exactly 25 people. Okay, so let's get our, this is obviously like a binomial distribution, success, failure, independent trials. So our n is number of trials, which 70 people are tested. Probability of success, well, that's choosing Quencola. That's 0.42, 42%. Q is 0.58, 1 minus P. And test our values, and P is equal to 70 times 0.42. That is 29.4. So obviously that's greater than 5, so that's good. And our NQ value will actually work out to even higher, 70. No, it's 70 times. So it's 70 times 0.58, which will be 40.6. And that's greater than 5, obviously. So those two tests show that we can go ahead and use the normal approximation. So let's declare a variable. X is the number of people choosing Quencola. Okay, and we want probably fewer than 25 people, so that's going to be probably that X is less than, to be careful here. So we're looking at 24, 23, 22, so less than 24.5 to do the continuity correction. Okay, and we want to convert that to a Z-score. So let's do that over here. I guess we have to get our mean and standard deviation. Well, the mean is NP, which we already know is 29.4. Our standard deviation is square root of NPQ. And again, I'll just get the final number there, 4.13. So that's square root of 70 times 0.42 times 0.58. Okay, and then the Z-score that we're going to use here, I'll call it Z1 because we're going to need to do another one. So Z here will be the X value, 24.5, minus the standard deviation, minus the mean over the standard deviation, and that's equal to negative 1.19. So that becomes our Z-score for 24.5. So plug that in here. And that's already set up in the right direction, so we just look this up on our Z-score table and we get an answer of 0.117. So therefore there is an 11.7% chance, or probability, same thing, that fewer than 25 people will choose Quencola. QC for short. Okay, so 11.7% chance. Okay, what's the probability that exactly 25 people? Okay, so hopefully you'll know how to do this one. This will be the probability that X is between 24.5 and 25.5 people. Using the continuity correction on both sides of 25. So we need another Z-score for the 25.5. So Z2 is 25.5 minus 29.4 over 4.13. That is a Z-score of negative 0.94. So this is equal to, change it to the Z-score notation here, negative 1.19 is less than Z, which is less than negative 0.94. You have to be careful when these values are negative because you have to think about where they are on the curve as to which one goes on the left and which one goes on the right. Sometimes it's not, you have to actually focus on the numbers before putting them in. Okay, and remember this, we break this into two Z-scores. Probably the Z-score is less than the higher one, which is this one, minus the probability that z is less than the lower. So probability that z is less than like 0.94 minus probability z is less than negative 1.19. Okay. And when we look up, I mean, we've already got the one value. The second value here we've already got here. If we look up this on our z-score table, we get 0.1736 minus 0.117, and that's equal to 0.057. So therefore, there is a 5.7% probability that exactly 25 people choose Quencoa. Okay. So hopefully after 3 examples, you've got a pretty good idea how to do this. Don't forget to do the check to see that that the normal approximation would be valid. That's the NP and NQ are both bigger than 5. You have to do that every time. And then you basically turn it into a normal distribution. We have formulas for the mean and standard deviations, and we use the z-scores using continuity correction because we're changing discrete data into continuous data. And hopefully after 3 examples, that makes a lot of sense. And you should try this technique out on these homework questions to get a good feeling yourself how to do it. So that'll be it for this lesson. And we'll see you on the next lesson. Have a good day.